In this video, we're going to talk about similar triangles, and we're going to apply them to right triangles, and how if we're able to anticipate the ratio of sides in a particular triangle, then we can solve some application problems down the road. So first, we're going to start with two similar triangles. Here we see triangle ABC is similar to DEF. And the first thing that we note is that all three sides in each triangle are in the same ratio, which is 1 to 2, and we tend to call that the scale factor. But instead of talking about the scale factor here, we're going to talk about the ratio of sides within a triangle. So, for example, if we take a look at the triangle to the left, what is the ratio of side AC to side BC? As you can see here, it's 4 to 5. So now let's take a look at the corresponding sides on the right-hand triangle. So DF corresponds to AC, and EF corresponds to BC, and the ratio of those two sides is 8 to 10, which simplifies to 4 to 5. So again, the scale factor of the two triangles is still 1 to 2, but now I'm just taking a look at the ratio of two sides within a triangle. And as you can see with similar triangles, that's a constant too. And here it's 4 to 5. And I could take any pair of sides as long as they're corresponding and the ratios would still be the same. So now let's take a look at similar right triangles. So here you can see two triangles. They are in everybody's favorite family of Pythagorean triples, the 3, 4, 5. And these also have a 1 to 2 scale factor. But again, we don't care about scale factor here. We're just caring about the ratio between two sides within the same triangle. So here we're going to look at the shortest leg to the longest leg, which in the left-hand triangle is 3 to 4. And then on the right-hand triangle, the shortest leg to the longest leg is 6 to 8, which simplifies to 3 to 4 as well. So you can see these two similar triangles also have the same ratio of two sides, as long as we talk about corresponding sides. Now, one way that I referred to these two sides was shortest leg and longest leg. But instead, we're going to reference these sides with respect to the angles. So if you look opposite the side measured 3, we have a 39-degree angle. So I'm going to, in the future, call the leg opposite the 39 degrees the opposite leg, and the leg adjacent to the 39 degrees the adjacent leg. And those terms are going to come in handy later. Now, if you take a look here, I'm going to draw another triangle that looks a lot like those two triangles. It's another similar triangle. And regardless of what the side lengths are, they're still going to be in a 3, 4, 5 ratio. Notice here I wrote 3x, 4x, and 5x, because it doesn't matter what x is. Whatever it happens to be, it'll remain in that 3, 4, 5 ratio. So if I happen to be standing next to a tall building, looking through a device that measured angles, and I looked at the top of the building, and my eye happened to be on the ground, if I found out that that was a 39-degree angle, and my eye was 100 feet away from the building, I know with certainty that the ratio of the two legs is 3 to 4. So if the bottom leg is 100 feet, or the leg adjacent to the 39 degrees is 100 feet, then the building must be 75 feet tall. And that's the kind of application that we're going to use here. So given an angle, we can then look up in a table the ratio of the legs, or it could even be the ratio of one leg to a hypotenuse, whatever it is. As long as I have that angle to input, I can find the ratio, and then if I know one of the side lengths, then I can go ahead and solve for the other side length. All right, now let's take a look at some vocabulary and define these different ratios. So here what I have is a triangle The capital letters are referring to the vertices, and they're a shorthand way of describing the three angles. The lowercase letters are referring to the length of the three sides, and usually that's what we use, lowercase letters for length, uppercase letters for points and angles, and typically we use the same letter for the sides opposite the angle. So notice little a is opposite big A, little c is opposite big C, and little b is opposite big B. And that's on purpose. So we're going to take a look at angle A here, and we're going to talk about each of these sides with respect to angle A. So little a is going to be called the opposite leg. Little c is going to be called the adjacent leg. And then B, regardless of what angle we're talking about, is always going to be the hypotenuse. Now notice everything's with respect to A, and we're going to see later if we're talking about angle C, the opposite and the adjacent legs are actually going to switch, which is really important. All right, now let's take a look at the three trigonometric ratios. We call these tangent, sine, and cosine. There are others, but these are the three that we're going to talk about in this class. The tangent of an angle is the ratio that's equal to the opposite leg over the adjacent leg. So that's what we were talking about in our previous example, that 3/4. That was the tangent of the 39-degree angle. In our triangle, the tangent of A is equal to the ratio of little a over little c. And the way that we would write that is here, little a over little c. The sine of an angle is equal to the ratio of the opposite leg over the hypotenuse. In our case, the sine of angle A is equal to little a over little b. And finally, the cosine of an angle is equal to the ratio of the adjacent leg over the hypotenuse. In this case, little c over little b. Now, again, these trigonometric ratios are all with respect to an angle. The angle is what we call the input of the function, and the ratios what we call the output. So if we know the angle, then we can look it up in a table or on a calculator, and it will give us what the ratio should be. And then provided we have the measurement of one of the two sides, then we can solve for the other one. So let's practice. Let's take a different angle. Let's take angle B. So starting with tangent, we're looking for opposite leg over adjacent. Well, actually, this is a trick question. We will never use sine, cosine, and tangent for the right angle in a triangle. We're only going to use it for the two acute angles. So we're just going to cross this off and move along to angle C. Now, if we take a look at angle C, which is over here, tangent is still opposite over adjacent, but in this case, little c is now the opposite leg, and the adjacent leg is little a. So this ratio is going to be c over a. The sine of angle C is going to be the opposite leg over the hypotenuse, which is c over b. And now if you look at my diagram, it looks a little confusing because adjacent is next to C and opposite is next to A. We're going to cross those off because those are only relative to angle A. Because in this case, adjacent is now little a and opposite is little c. So it's important that you always know which angle is going to be the input of your function. All right, let's finish these out and look at the cosine of angle C, which is little a over b. And then in the next video, we're actually going to use these ratios to solve for unknown side lengths in right triangles, provided we know the measures of each of these angles. Very similar to the example that I showed you about solving for the height of that building.